Hello, welcome to our final milestone of our project. We are presenting to you today the overall progress of our project, which is about image restoration. Our main problem is that we have historical images, they have noise, and we'd like to fix this issue using deep learning and remove all of the noise as shown in this photo in order to have a higher resolution.
Okay, so originally the paper that we used consisted of using a CNN model as spoken previously. This DNCNN model uses a Gaussian filter of 64 filters to be precise. It uses a depth of 17 layers. The initial layer is convolution and relo. The remaining from 2 to 16 layers were convolution, batch normalization, and relo, with the final 17th layer being convolution layer. The input is obviously a noisy image, and the output is a residual image, along with we later on, the output here now is only a residual image. So the data set they used mainly was Train 400, which consisted of grayscale 180 by 180 pixel images, and they were a total of 400 images.
So what we've made changes for the original architecture was adding dropout layers in some of them. We had the iterative layers, which consisted of a convolution, batch normalization, and relu. We added dropout to that before going through the last convolution layer in our model. We also changed the data set that enters the new model because we wanted to improve on that and support RGB images, three-dimensional images, as long as heterogeneous images too. So they didn't have to be 180 by 180 or squared images. So we used the diff2K dataset, and we had them to be noisy in order to test the model and train it to enhance this and remove the noise that they have.
Okay, so the results were as follows. Firstly, initially, we printed out results of grayscale images, and as you can see, the noisiness decreased incrementally. Of course, the result is not perfect. However, the noise decreased with a great amount, as you can see. So this is an image of a dog before and after using the model. And this is another image, also grayscale. Notice how the features are also smoothened along the way while removing the noise. Also, moreover, you can see
we have over here the RGB, so that's the output of the model after making it supporting the three-dimensional images. So on the right-hand side, we have the output of the model, while in contrast with the left-hand side image, which is the noised version of the diff2K dataset. This is another example. You can see how the noise has decreased along with the edges of the wall that we can see over here has smoothened out. We actually found out that the loss has decreased while we improved the model. And initially we had the original model had a loss of 155, while ours had a loss of 160. I'm sorry, I apologize, the other way around. Ours has the 155 and theirs is at the 160. So those are the graphs for or the plotting for the training loss the original model versus ours. This is another plot that we had during our training. You can see that they're both quite similar. It's just that the loss was started at a very high point, which was greater than 2,500. That's because when we use the RGB, but then it plateaued off until I guess 170.
Okay, so now one of our proposed solutions or one of the things that we were supposed to do or implement in this milestone was to evaluate the metrics using PSNR. And this is a plot of the PSNR versus the epochs. We iterated over, 100 epochs. However, it is obvious that the model begins to converge at around 41 point something. Around 41.7 PSNR, which is the peak signal to noise ratio. This is the metric that we decided to use, and this is the metric of this current state of the art that is being implemented when trying to evaluate noisy images in general. So in conclusion,
We can have the demo beforehand.
Okay, so before so just a second. Let's open the demo. Okay, it's fine. Okay, so now as you can see, this is the terminal, and we're going to run our test a few images right now with you. And let's see what happens. Okay, there we go. The system is running and it will print now a few images. As you can see, this is the image that was presented in the presentation initially. This is the output in better or precise details. We'll also try to show you a few other images as well. This is one of the images in X-ray mode.
Fun fact about this image is that we found the noise image on the internet, so it was completely random.
Okay, this is another image. If you can just want to say it more precisely. As you can see, there's a lot of noise on this, I don't know, C-star. And you can notice here how smooth it is. Also notice the noise that's found here and here. It's clear and here as well. Okay, let's show the rest of the images really fast. This was also on in the presentation. And I guess that's it for the demo. Moving forward to the conclusion in general. So in conclusion, our model was able to enhance the noisy RGB as well as the grayscale images of different sizes into high resolutions, of course, with the help of a DNCNN model that uses 3 channels. And as spoken previously, with adding padding for any heterogeneous image sizes, as well as implementing the PSNR metric. And as you can see, this is a different image. Was a quite high quality image, but you would notice that there are still minor differences between even the black and color.
So what we find, if we had the opportunity or more time to implement this, we would have actually improved accuracy further, so as in to remove any further noise, so to have the image very, very clear. Also, we thought about expanding the idea of the project itself to accept videos instead of just images or even colored images. So something 4-dimensional and reduce its noise, that would be very nice to do. And also we have the medical scans. If we do concentrate our data set into one thing, as if an example for the medical scans, that would make it very useful in the medical area.
Okay.
That's the team member contribution for each one of us, and thank you very much.